Okay, I want to talk about two more kinds of sounds that we can make, and we'll examine the second one in more detail on Monday, which will lead into the first assignment. So first I'm going to talk about something called a chirp. So in the equations that I had above, where I said for a sinusoid, I said f is equal to a times cosine 2 pi ft plus phi. I'm going to tweak this equation a little bit, and I'm actually going to make, let me change this instead of f of t, I'll change it to y of t, just so we don't have a collision of names here. I'm going to change the frequency to actually vary with time. So the equation is basically the same, except frequency does not have to be fixed. Frequency can change over time. But just as an example of this, so this is something called a linear chirp, or an instance of that. So if I have something like f of t is equal to 440 plus 440 times t, yeah. Then let me just plug that in. That'll give me y of t equals, and I'm assuming amplitude 1, no phase shift, so I'll say cosine of 2 pi 440 plus 440t times t. So if I simplify that'll actually be y of t equals cosine 880 pi times 1 times t plus t squared. I think I simplified that correctly. Okay. Okay, there we go. So let me write this in code. So I'll say t is equal to np.linspace. So I'll make a second of audio here. 0, 1, and I'll make SR samples. Let me actually, I'll keep it in this form. So I'll say then the frequency, it's supposed to start in this example at 440 plus 440 times t. So when I'm a second in, it should be 880 hertz. So now I'll say y is equal to cosine of 2 pi f t. Okay, but now f is actually changing. F is an array, not just a single value. So when I multiply f by t, it's actually going to element-wise multiply each frequency at each time. Okay, so let's listen to this. All right, so that was interesting. so this is something that goes up in pitch as we move through time. Now we could, okay, so t is going between 0 and 1. If we raise t to a power, it will go up more slowly at first, and it will, if this power is greater than 1, and it will rise faster at the end. Okay. So that is no longer a linear chirp. Let's go back to linear chirp. Okay, that's our linear chirp. Okay. The other thing I want to show you is something called a beat frequency. So this is the interaction of two cosines with each other. I actually want to do a little bit of plotting here so I can show you what the deal is. So let's say, all right, one frequency is, now since I'm plotting, I don't want to go to such a high frequency. Let me say, I'll say 5 hertz, and the other one is 6 hertz. And I'll, maybe I'll look at like 400 samples between 0 and 1. So I'll say y is equal to np.cosine f1 2 pi f1 times t plus cosine 2 pi f2 t. Now we've listened to the superposition of cosines already further up here when I added at some point. Yeah, when I added these two together, you could hear it. I think that was when I had that interval of a fifth, right? So I had the A and then I had the E, and I added those together. But I didn't really look at what the waveform actually looks like when I did that. Okay, and actually, let me go a little further. Let me go, have this go through more cycles. Okay. It's probably also helpful if we look at the originals. All right, so let's see. I'll do 10, 14. So I'm just going to plot. Yeah, let me actually separate these out into two different sinusoids. So I'll say y1 is equal to that first one, and then y2 is equal to the second one. Plus y2. Okay. So let me just plot these individually first. And then below that, so you can actually put more than one plot in one. Below that, I'll plot the superposition. Oops, I meant to say 2, 1, 2. There we go. Okay, and actually, I guess I will zoom in a little bit on. I'm having a hard time deciding how many periods I want to go through here. Let me say, or how many seconds I want to go. Actually, you know what? Probably 3 is enough. Okay. So you see these two together. They start off in the same place, but the orange one goes faster than the blue one. At some places, the orange one is actually positive when the blue one is negative. You see that? And vice versa. So here the orange is positive when the blue is negative. Here the orange is negative when the blue is positive. And so when that happens, they actually cancel each other out. But other places, they line up. So you see here, they line up pretty nicely. So when they are the opposite of each other, they do something called destructive interference. When they line up, they do something called constructive interference. And you notice here that they start off constructive, but then they cancel each other out. But then they go constructive again, and they cancel each other out. And then they go constructive, and they cancel each other out. So you get these what are called interference patterns. And let's see. Let me make them even closer to each other. So let me make this like 5.8 hertz. And here you see something very interesting. So if I zoom out even more, yeah. So now is where I think I want more seconds. So let me go to like 8. So you see here, it looks like it takes a lot longer for it to become destructive. So it's a slower process. They're lined up because they're much closer to each other in frequency. They're lined up for a lot longer before they become out of alignment. Okay. So anyway, that's what you can do when you have two sinusoids added together. Now, why is this relevant to digital audio? Well, let me show you. So I'll do this same sort of thing, but I'll actually go to audible frequencies now. So let me make this maybe 440 hertz, and I'll make this, let's say 445 hertz. Okay, and then I'll make T go from 0 to 1. So I'll make 1 second of audio with as many samples as there are in a second. And now I will listen to this. Okay. So what did you hear? So these are very close together in frequency. Let me make them even closer. Let me make them maybe 440, 442. Maybe it'll help if I make just a little longer audio as well. Okay, so let me go back to, so I'll do 4 seconds of audio now. And let me go back to 440 and 445. All right, and now let me go to 440 and 442. What about 440 and 441? So, what are you noticing as this happens? Take a moment and think to yourself. So what do you think would happen if I made this 440.5? So what you should be noticing is that the difference between these two frequencies creates its own frequency of sorts. And this is called the beat frequency. Okay, so the beat frequency is F2 minus F1. And that is the frequency of the constructive and destructive interference. So the closer they are, the lower the beat frequency is going to be. If they're far enough apart, you don't really hear it like a beat frequency anymore. So if I make this like 480, so that sounds like a ringing telephone. I guess, yeah, I mean, there's a beat, but you don't really hear it like that. And you know, if I go even further up to like 660 again, you know, I'm not hearing a beat there. Okay, but when you get close, that's when you hear it. And the frequency is the difference between the two. So we're going to use this for artistic purposes in the first assignment. We're going to create compositions using beats. So we'll start to explore that on Monday. But this is like one of my favorite concepts ever. This is also how theremin works behind the scenes. And this concept is used a lot in radar. Actually, chirps and beats are used together in radar. It's very, very cool to do ranging, to figure out how far away something is, and sonar as well. Okay, so thank you for attention. I will see you on Monday.